Hello everyone, I'm glad to introduce our work, Improved Visual Fine-Tuning with Natural Language Supervision. I'm Jun Yang from Beijing Jiao Tong University, and I'm an internship of Dharma Academy Alibaba Group. This work is about visual fine-tuning, and it is a very popular method. Fine-tuning transfers the information from pre-training data to target task, and it mitigates the overfitting problem. However, the bias from pre-trained model limits the transfer performance. The distribution divergence between the pre-training data and the target data makes the transfer difficult. Unfortunately, the bias can cause the misclassification. In this case, the bus and tank are similar in pre-training data, so even we fine-tune the model, there is still confusion between the two classes. So how to mitigate the bias? Can we mitigate by setting learning rate? First, if we increase the learning rate, the model will suffer from the catastrophic forgetting and overfitting problem. This is because the large learning rate makes the fine-tuned model far away from the pre-trained one, and the fine-tuned model will forget the information from the pre-trained model. Although this work introduces additional data to avoid this, however, this requires access of the pre-trained data, which is infeasible in many real applications. So it is useful to keep a small learning rate. We prove that it doesn't work. First, this is a standard fine-tuning process with a small learning rate. We prove that the proxies of the classes in classifier are constrained by a small learning rate of the backbone. So traditional methods can't solve the bias problem. In this work, we introduce natural language supervision to fine-tuning a model. This is because test information is helpful for guiding visual representation learning. For example, the bus and tank are similar in vision space, but distinct in text space. So we first extract a reference distribution Z from a text encoder by the class name. And then we use a class-level method to align the proxies of fine-tuning model and the reference distribution. Finally, we simplify the KL divergence and the optimization is like this. However, class-level method doesn't take into account the differences in the instance. For example, in the class-level method, a cat that is like a dog will still be a cat. To allow for more flexibility, we introduced the instance-level method that generated the corresponding reference distribution for each instance. We replaced the proxies by the representations of instance and optimism projection head to align the representation to the reference distribution. Finally, the text-supervised fine-tuning can be cast as this. One part is vision fine-tuning and the other part is text projection optimization. We show the improvement on wire backbone. First, we show the improvement on ResNet 50 pre-trained by Moco V2 and the ResNet 18 pre-trained by ImageNet. Then we show the improvement on VIT pre-trained by MAE and CLIP. Finally, we show the improvement on few-shot condition and long-tailed condition. We can see TAS has significant improvement on various backbones and conditions. We also show the illustrations of the reference distribution. We can see that TAS is more similar to the CLIP. For example, the confusion of bus and tank disappeared in the test, which is guided by CLIP. Thank you.